So I'm going to start talking about non-right triangles. So I don't want to emphasize what goes wrong. Let's talk about what goes correct for a right triangle. So suppose I tell you that this is a right triangle. Side length A, side length B, right angle, hypotenuse is C, there's an angle B and an angle A. Tell me something about that.
It's a right triangle.
It's a right triangle? Yeah.
Angle B and A add up to 90.
Cool. If you happen to be in degrees, in radians, I guess it'd be pi over 2. But what else can you tell me?
A squared plus B squared, C squared.
What else can you tell me? Maybe something involving a trig function. And I guess there are like 6 different things you could tell me. Sine, cosine, tangent, and at A or B. Let's write down one of them. Tell me a trig function value you could evaluate using this triangle. Just pick one.
Sine AC.
Cool. Sine of A. Using that triangle, what can you tell me about sine of A?
8 over C.
Cool. And then like 6 more of those. Those are only true for right triangles. If that angle's not a 90-degree angle, none of those things happen. Oh, none of those things have to happen. They might accidentally happen, they won't. So I want to start building analogs for what if that angle, that right angle isn't a right angle anymore? What if instead I give you something and that angle's like 98 degrees? It's still pretty close to a right triangle, so all those things are probably pretty close to true. But how far off are they? That's what I'd like to start with today. And maybe I'll start with one last fact. What is the area of this triangle?
1/2 AP.
Because that's like half of a rectangle. And that's also important that this be a right triangle to read that off. If I gave you same side length B, same side length A, I guess the side length C will be different. And I tell you that this angle's like 130 degrees. That side length C, there's an angle A, there's an angle B. None of those things will be true. I want to find like things that tell us the same type of information, but when there's not a right angle to walk with. And the first one I want to start with is the area formula. So here's the first formula I want to start today with. Theorem. The area formula for a non-right side angle side triangle. So if I give you a triangle, I tell you that side length, and that area. All of those things are things you know. Then the area is given by 1/2 B C times something that accounts for something. Right, like if this angle A were a right angle, you would just have 1/2 BC, right? It's not a right angle. And so the thing that accounts for how far you are off is the sine of that angle. Well, let's do one sanity check real quick. So if that angle is a right angle, then I should just get 1/2 B times C. So let's check that. What if alpha is a right angle? Well, let's see what this formula would say then. This would be 1/2 B times C times sine of radians or degrees. What would we rather walk in right now? Sure.
Actually, no degrees.
Degrees, cool. If you want to work in radians, great. What's the degree measurement of a right angle?
90.
Cool. So this should be 1/2 BC sine 90 degrees. What's the sine of 90 degrees?
1.
1. And you better not have needed your calculator for that.
Let's double check.
Okay. Because right, like that's like maybe the most important angle to just know off the top of your head. Maybe 0 is more important. Cool, so that should be 1/2 BC times 1. Oh yeah, that's the area formula you expect. And I'm not going to try to give you an argument for why that's true. There is an argument for why this is true in the other important formula of the day in an extra credit, which I'll point out in a moment. Let's use this to do one more computation. Here's a triangle. It looks pretty non-right. Does that make it wrong? Do you think you can compute the area of that using this formula? Yeah, cool. I guess I'll give you options. I do, or I be quiet and you do. Should I do? Cool. So let's apply this formula. So the area is 1/2 b times c times sine of a. So if you just match up symbols in this triangle, what's b? Well, it should be one of the two known sides, right? So give me a length of one of the two sides you know.
4.
Give me the other length.
2.
Times the sine of the angle at which they meet.
5 or 8.
Pi over 8, is that an angle you know on that you already know because of the unit circle? I mean, it's not. You know pi over 4, you know pi over 6, but not quite pi over 8. We will be able to compute trig functions at pi over 8 by the end of the semester, but not yet. So let's just simplify that and then we'll get a decimal approximation. So simplify it, what do you get?
4 times sine 5 over 8.
Yeah, cool. And let's suppose that you actually care about the bigness of the area of the triangle. Let's get a decimal value for that. Maybe round to the nearest, I don't know, 100th? Yeah.
1.53.
Cool. And there are no units in the problem, so there's no units in the answer. Neato, feel pretty good? So you can use this to understand areas of triangles. And we'll use this a few times throughout the day, so keep that formula in mind. Maybe I'll even put it on the board. Here is the first of the formulas for today. And I'm going to fill in this diagram some other angles. And you'll notice I'm sorting the angles alphabetically so that the angles are all lowercase, the sides are uppercase, and otherwise they're just opposite each other. That's going to be important for the next statement. So here's the next statement. The law of sines. If I give you a triangle whose side lengths are a, b, and c, angles little a, little b, and little c are opposite the side lengths with the same name, then you get the following equations. If you take the sine of one of the angles and divide by the side length opposite, you'll get the same no matter which one you pick. Cool. And I'm not, again, not telling you why that's true. I'm not giving you an argument. I'd rather use this to do some computations. And to do those computations, it's often useful. Right, if that equation's true, then I could flip all those fractions upside down and they'd still be equal to each other, right? Just take the reciprocal of each one. Sometimes it's useful to have that as your starting point too. I'm going to put that on the board. And then we're going to use that on the next page to make some more computations. So, area formula. Next fact that's important is the law of sines. And you know what, maybe before that, let's make the sales pitch for the bit of extra credit. There are like 2 extra credits associated with today. Here's the first of them. It's a long section of the notes. So we've written down that area formula on the law of sines. I haven't told you why they're true. The area formula is just true because you can study this sort of formula and read off the area of that triangle, right? It's 1/2 base height. So if you can compute the height of a triangle by using some trig functions, then you can use 1/2 base height to prove the area formula. That's all that comes from. So go through this. That's like half of an extra credit for today. The other half of the extra credit's on the next page. If you know the area formula, well, you could use the area formula using those 3 numbers, right? You could use the area formula using those 3 numbers. They should give you the same answer. That's why the law of sines happens. Compute the area formula 3 different ways, set them equal to each other, and like rearrange the equation so that you sort the information alphabetically. Hey, you're just proving the law of sines. Go through those 2 things, come talk to me, that's an extra credit. But for now, let's use those to do something. So here's the most obvious application of the law of sines. Is it like slightly out of focus? Let's try to adjust that. That's a little better, right? Maybe. Here's the main application of the law of sines. And it's an application that's a warm-up to something that we'll explore a lot in the coming days. If I tell you 3 things about a triangle, then probably I've told you what the triangle is. There are some like edge cases and some weird things that can happen, but usually if I tell you 3 things about a triangle, you know the triangle. And here's one of those examples. Let's suppose I tell you an angle, and a side of a triangle. Any 2 angles and any 1 side. I claim that that's enough information that we can figure out what this triangle is. We can know all of the angles and all of the sides. We could compute the area because we know all the angles and all of the sides. You compute the perimeter, but whatever, that's enough. Let's try to do that. Let's take this triangle and let's just try to figure out everything about this triangle. What seems like the easiest thing to discover given this information?
Angle B.
Angle B. Nice. What's the thing that lets you compute angle B?
All angles equal 180.
Yeah, if you add up the angles, you'll get 180. So I guess in that case, that means 20 degrees plus 25 degrees plus the angle called B has to be 180 degrees. If we were in radians, they'd add up to pi, but that's fine. Oh, cool. So can you tell me what B is?
135.
I hear a 135. God damn it. Spam is spam. Sorry about that. Neato. Oh, cool. Let's also note that. Is that an angle that you know on the unit circle? Pull out your unit circle if you need. Say louder.
Is it 500 or 600? 354.
Cool. So keep your unit circle handy. We'll use it in a moment to do some computations. So let's start determining the sides. So here's how you use the law of sines when you want to like do this sort of stuff. Is there a pair consisting of a side and an angle opposite that we know? Yeah, it's this side and that angle opposite we know. So let's write down what the law of sines tells us. Law of sines. I'm going to leave the left side of the equal sign blank for a moment. It tells me that lots of different things are equal to 4 divided by the sine of 135 degrees. And let's suppose you wanted to know the side length A. What equation could you write down because of the law of sines now?
Sine of 135 over 4 equals sine of 20 over A.
Yeah, nice. I'm gonna write it upside down though, because that'll make it easier to solve for A.
Good enough.
Like what you said wasn't wrong, but there'll be an extra step you'll have to do where you take the reciprocal, so I'm just gonna take the reciprocal first. Nice, so don't actually do it yet, because I'm gonna do some simplification first. That look like an equation that you could solve for A? Yeah, in fact, I guess the one sentence somewhere is like cross multiply. Before we do that though, before you do algebra or something, let's try to simplify it. We know what sine of 135 degrees is. What is the sine of 135 degrees?
It's root
Root 2 over 2.
Yeah.
So this is equal to 4 over root 2 over 2. That's certainly simpler looking in that now there's not a sign on the right-hand side of the equal sign. Should that be simplified more? In fact, maybe I'll ask you, should I go through the walk of simplifying or should I be quiet and let you simplify? Should I do? Cool, but I'm going to wait a bit, and once you have it fully simplified, you will tell me what the right-hand side of that equal sign becomes. Once you have that fully simplified, let me know. Maybe more than that. Once you have it fully simplified, compared with someone around you. Cool, and right here. Right here, 4 root 2. I'll give people some more time to either conform or deny.
Yeah, it's but because I was trying to cross multiply, it just isn't like a cross multiply. It's like you take the equal side by this, so it's by this, right?
Yeah, cool. That's not quite so simple, man. Is there a common factor between the top and bottom?
Yeah. Just awesome. Both sides, that's root 2.
Nice. Let's talk through it. So I think I've seen a second for 4 root 2 now. So let's go through the walk. How do you? What's the sequence of simplification moves? Where did you start on this?
Multiply by reciprocal.
Nice. I see a fraction in the denominator. That's something I don't like. That's 4 times 2 over root 2. All right, what next?
Cross multiply.
What do you mean by cross multiply?
Multiply.
Ah, okay, just 4 times 2 in the numerator. So I guess that's 8 over root 2. Okay? What next?
Multiply by square root 2 over 2. Square root 2.
Nice. I don't like that there's a root 2 in the denominator. I can change the form that this thing's in without changing what it is by multiplying and dividing by 1. And let's see what that gives us. What's the numerator now?
8 root 2.
Denominator?
2 root 2.
Nice. Root 2 is root 2 squared. Squares undo square roots. So how do you go from that to 4 root 2?
Divide by 2.
Divide by 2. 8 divided by 2 is 2. Cool. That feel good? And like super familiar, right? Like we've done that sometimes. Can't people maybe just recognize that root 2 over 2 is the same as 1 over root 2? You could have. Would have made things shorter, I think, because then... Anyway. All right, so that means that we now have A divided by sine 20 degrees equals 4 root 2. And now, like, the simplification was the hard step. The algebra is the easy step. Solve that for A. What do you get?
Got like, I got 16.
Say that R.
I had like 4 sine 20 over the square root of 2 over 2.
Nice. So it'll be. So you're multiplying sine 20 to the other side?
Yep.
So you'll have 4 times the square root of 2 times sine 20 degrees. Cool. I feel all right? Nice. Could we do the same thing to find the other missing side? Yeah, let's write down the equation we get. I see A divided by, nope, not A, we found A. B divided by the sine of the angle opposite B. What's the angle opposite, nope, not B, C. C is the missing side, Jesus. What's the angle opposite side length C? 25, and I'm going to always write degrees because otherwise I'll get confused and think that it means radians. All right, and let's use the same pair. 4 over sine of 135, and again, let's simplify, but we've already simplified. What is 4 over 1? Yeah.
Oh, I just have a question. What determines whether the angle is in the numerator or denominator? Does it matter?
Whichever one, as long as you're consistent. As long as it's always sides on top and always angles on bottom, then you're fine.
Okay.
Or always angles on top and always sides on bottom. Because it's the same equation, right? I can take the reciprocal of both sides of an equation. It's a matter of convenience. Right? If instead I saw the same thing but upside down, I'd have to start by getting C out of the denominator.
Okay.
Which, this way it's already out of the denominator. So, this is why I wrote down both, because like sometimes one is more convenient than the other. Both will get you to the same end goal, but if you use the wrong one, you'll have an extra step. Cool. People feel good? Let's do it. What did we just simplify 4 divided by sine of 135 degrees to be?
4 over root 2.
Oh, cool. So this is like basically the same equation again, right? So, what's the exact value of the side length C?
4 root 2 times sine 25.
Yeah, cool. You just need to multiply sine 25 degrees to the other side. Alrighty. That's not bad, right? And I guess it's handy that it's been quite a while since we've talked about Descartes' law of sines with a G, because this is also the law of sines, isn't it? Just without a G. So let's talk through like the general philosophy and how to solve a 2 angles and a side triangle problem. What's like the general thing we did? Step 1 was figure out the missing angle. Use the fact that angles sum to 180 degrees, or sometimes we walk in radian modes, right? Or pi radians to determine missing angle. There's like step 1. Oh yeah, absolutely, thank you. And after that, we need to do something to determine the unknown sides. And how did we do that? We used, well, the law of sines, which says that if you take any of the missing sides, and divide by the sine of an angle, that's equal to the known side divided by the sine of an angle. And you can use that and now solve for the missing side. You know all the angles. That feel like a reasonably straightforward application? Nice. And it's actually like a really important application. This unlocks a lot of important trigonometry for lots of applications. And I'd like to visit one of them by redoing some of the like surveying problems from a while ago. So you remember the like bit of shtick I did in class where I brought in like that Abney level and like we determined the dimensions in the classroom? It was like really important in that process that my feet were at the same height as the back wall, right? Because I needed a bunch of right angles. If you don't know that the thing you're standing at the same height as the thing you're trying to measure, there could be some dodginess. You'll be assuming some angles are right angles that like just aren't. And like that actually usually happens. Right? Like if you go and try to measure the height of a building on campus, well, how flat is the ground on campus? Yeah, reasonably. I mean, I did my undergrad in Utah, so like it's pretty flat. Like I definitely couldn't have used that technique to measure any of the angles on the campus where I was, because like the campus was at a pretty solid, like 5 to 10 degree slope. So you just can't use it. But this is exactly the technique you need for a non-right triangle. So let's try to repeat all of this, all of the stuff about measuring dimensions of things, surveying. So here's some setup. You've got something really tall you want to measure on. Maybe it's a building, maybe it's a tree, I don't know, maybe it's a mountain, maybe it's Godzilla. So here's the strategy you're going to use. You can't use the strategy we did before because like you don't know that you're standing at the same height as Godzilla. Maybe he's on a hill. Is Godzilla canonically Gendon? They're on a hill.
If I recall, isn't it like, doesn't it language would imply that it's a female? Or...
Good enough. This is an important discussion right now. She's on a hill. You stand an unknown distance away from Godzilla, and you measure a few angles of elevation using an Abney level. You measure the angle of elevation to the bottom of the building or the feet of Godzilla, and I've just provided some numbers to be 5 degrees. You also have a friend who has a 2 meter tall measuring stick standing in front of the thing you would like to determine the height of. You are also going to measure the angle of elevation to the top of that 2 meter tall measuring stick. Um, 10 degrees, is that what it says? 2 meter tall stick, basically 10 degrees. And then finally, you measure the elevation to the top of Godzilla's head, or the top of the building, and you get 55 degrees. And let's also include one more thing in this. I know that this length is 2 meters. And let's remember the philosophy of this like non-right triangle trigonometry. If I can find a triangle here that I know 3 things about, then I can figure out everything about this triangle. I guess one of those things has to be a side length. And right now the only side length I know is that 2 meters. So let's pull out that triangle and see what we can say about that. That side length is 2 meters, it's that 2 meters. What else can you tell me about that triangle? What other angles can you tell?
5 degrees for where you
Nice. This big angle is 10 degrees. 10 less 5 leaves me with 5 degrees. All right. Could we determine other angles? And maybe let's just take the whole original triangle, the big triangle, and let's just determine any of the angles we can in there. So, I guess tell me an angle that you can determine. Yeah.
The angle from you to the top of the building is 35 degrees.
Nice. So like, are you saying this angle or which angle? This one?
Yep.
Okay. Nice, because it should be this plus this is 90 degrees. So, yeah, that checks out. Yeah.
The triangle, you can find the top angle there.
Cool.
100, 80 minus 95. It says it's right angle there.
Yeah, that's a right angle. And like, if you just extend those to like the horizontal line, I'm not like measuring it, it's apparently underground.
I didn't actually do the math, it's just 180 minus 95.
85? 85. Yeah, right, because 85 plus 5 is 90 degrees. Okay, cool. So what other angle could you tell me? Yeah.
The angle from you to the top of the building is 45 degrees.
This angle is 45 degrees. Yes, any other angle? Yeah.
In the triangle we're trying to find, between the measuring stick and the bottom of the building, you can find that angle. 180 minus 85.
180 minus 85 degrees.
So I'm assuming it's just a straight line there.
Yep.
So, yeah.
So that'll be 95 degrees because this angle plus that angle has to add up to half of a full revolution. So that'll be 95 degrees. Let's put that here. Yeah.
From when I did for the angle from you to the top of the measuring stick is I got 80 because it's basically triangle. You have one angle that's 10 degrees and one that's 90.
Cool. 10 degrees, 90 degrees. So you're saying this angle should be, just say that again,
80.
80 degrees. So that means this angle should be 80 degrees. Cool. And let's just do a quick sanity check. We computed those angles different ways. Let's reflect on the triangle we're interested in.
So we're,
Do those angles add up to 180 degrees now?
yes.
Awesome. And now let's focus on this triangle. I know all the angles, and I know a side length. Yeah.
You do 2 over sine of 5 equals x over sine of 80.
Nice. 2 divided by the sine of the angle opposite. Equals unknown side length x divided by sine of
80.
Oh, cool. And let's do a quick check for simplification. Are any of those angles that appear on the unit circle? Cool. So there's no simplification we can do. We're just going to have some signs in our final answer. We'll get a numeric a decimal approximation at the end. Oh, cool. So solve that for x. What do you get? Should I solve it for x? Then I will do. So there's the thing that law of sines tells us. The side length 2 was opposite 5 degrees. That's where this came from. The side length x that I want to know is opposite 80 degrees. So I guess I can just multiply the sine of 80 degrees to the other side. So I'm seeing x is 2 multiplied by sine of 80 degrees divided by sine of 5 degrees. And we can get a decimal approximation now just for the sake of context, but I don't think I really care about it. Yeah,
I got 2.07.
I hear 2.07. That seems a little low.
That might be that's in radians.
Oh, yeah, okay.
2260.
Nice. And I'll put the units back because, like, that's maybe a number that in some other thing we're going to care about how big it is. I think I don't immediately because I care about the height of the building or whatever we're measuring. Okay, so now I know this, nope, not that side length. I know the length to the bottom of the measuring stick. Could we also figure out the distance from you to the top of the measuring stick? We could, but I think I don't care about that side length. Right, my goal is knowing this side. Cool, so that triangle, the one whose edge I just highlighted, do you now know angles and at least one side? All right, let's copy it down then. I think I want to make up a variable name for h. What variable name should I call that side?
Y.
I hear a y. I also hear an h. Fundamentally, it doesn't matter. Maybe I'll use h because h doesn't have any other jobs yet. If you want to use y, use y. If you want to call that variable name smiley face, do it. Follow your heart. All right, so let's fill in some things. I know one side because I know what x is. X is that. And I think I'm just going to leave it as x. I know what it is, but I'll just remember that I know what it is. Let's fill in the angles. What are some angles in this triangle that you can tell me? Yeah,
Angle from you to the top of the building is 50 degrees.
cool. So this angle?
Yep.
Shouldn't it be 45, since that's what we have in the triangle on the top? Yeah.
Let's try to decide.
I think
Oh, I know, 50 is right, yeah, that's my bad. It's 50.
Do I hear a call to discuss why 50 and not 45? Cool, then I will. So I certainly see this 45-degree angle here, but that's the angle up to the top of the measuring stick. I want the one to the bottom of the building. So I actually want this angle, which is, well, goodness. That's a 5-degree angle. This angle was a 5-degree angle. So yeah, it'll be the 45 degrees plus an extra 5 degrees. All right, other angles in this picture. This one, what's that angle? Nope, you're measuring it at the wrong spot again.
95.
Yeah, because it's this angle, right?
Oh, you're looking at that.
Yeah, the 100-degree angle would be like there. So if you wanted to measure, oh, well, I highlighted the wrong side. Hmm?
Isn't that the one that they're gonna find right now?
No, I highlighted the wrong thing. I want the whole height of the building. If you use that angle, you'd have to add 2 meters in the last step.
Okay. And 35 for the top angle.
And 35 degrees for the top angle. All right, cool. Is this enough information for us to walk with? Let's do it. H is the thing I want to know, so let's start with H. So it should be H divided by
Sine 50.
sine 50 degrees. What's the name of the side that I know?
X.
X. And you can replace it if you want with 2 times the sine of 80 degrees divided by the sine of 20 degrees in this step, but I think that would just result in lots of things being messy earlier than they need to be. And what should that be divided by?
Sine of 80.
Sine of 35.
I think sine of 35, right? Here's the side length x, its opposite, 45 degrees. All right, and I want to know what h is, so let's solve that for h.
X times the sine of 50 over sine of 35.
Groovy. But I also know what x is, so let's substitute that in now just to like get the answer all the way written down. So maybe I'll even color code this step. X will be in pink now. So I want x, which is 2 times the sine of 80 degrees divided by sine of 5 degrees. I want that times the sine of 50 degrees divided by sine of 35 degrees. I notice that I wrote those in a way that like isn't what you get if you just copied down x where it is, but is that the same as what you would get if you did? Yeah,
Why is it not the, why is it not the sine 35 just beneath all of it?
Yeah, so let's write down what we get if you straight up write it down verbatim and then simplify. So let's put down what x is. X is 2 times the sine of 80 degrees divided by sine of 5 degrees. All that multiplied by sine of 50 degrees. All that divided by that, sine of 45 degrees. So that's what you wanted written down?
I just want to try to simplify it from it.
Yeah, so let's simplify from there. So all that we see here is multiplication and division. Does it matter which order you multiply and divide in? Right, like I could move this to that numerator, right? So then you'd see 2 sine of 80 times sine of 50, then divide by sine of 5, then divide by sine of 45. So you could write it with a single denominator now. So if you do that multiplication law, you'll get 2 sine 80 degrees times sine 50 degrees. Then you divide that by sine 5 degrees. Then you take all that and divide it by sine of 45 degrees. Do you buy that? And if you divide by something and then you divide by something else, you could just divide by the product. Right? Like if I divide something by 7 and then divide it by 8, I could have just divided by 56. Or whatever 7 times 8 is. 7 times 8 is 56, right? Okay. So that's the same thing as 2 sine 80 degrees sine 50 degrees.
Yeah, see,
Oh! Divided by sine 5 degrees sine 45 degrees. So I guess the hard step was at the very end where you like just have to simplify a bit. The actual geometry and trigonometry wasn't the hard bit here. So let's now close this out. I probably want like the actual like numeric height of this building. About how tall is it?
I'm forgetting.
Hmm? Am I forgetting something?
Don't we need to, like if you go up to that picture, yeah, I still can't see.
Oh, sorry.
So we know 2 and we know H, but we still don't know from the ground floor to the top of the building, right? Or to the measures.
All of that was H.
Yeah, what about
Oh, this last bottom
90
bit?
degrees up, yeah.
Oh, well that's like how tall is the hill that Godzilla's standing on, which isn't what I wanted. Godzilla was already a little bit above me, and so I'm already looking slightly up to get to Godzilla's foot.
I need reading comprehension then.
Yeah, maybe, maybe not. Hopefully the wording is clear enough. I want the height of the building, so that's like from the bottom to the top. Which,
Or just to read.
I don't know, like what does one mean by height? If you measure a building and it's on a hill, should you include the height of the hill and the height of the building? You should just be clear. How big is that?
30.18 meters.
Groovy. That feel pretty good? All right, sales pitch for extra credit. You remember the Abney level that I brought in? It's still sitting in my office, along with a few tape measures. So come by my office with a friend, or at least someone you can stand walking with. One of you is going to stand by a building on campus with the tape measure out to a fixed height. The person with the Abney level is now going to measure the angles, just as in this example. I guess the tape measures I have are all in imperial units and not metric, so you know, you won't be in meters, which I find aesthetically displeasing, but what I bought were the cheapest tape measures that money could buy. Determine for me the height of one of the buildings on campus using this. And you'll get a more accurate result than if you use the technique from earlier in the class. All right, I have 3 minutes left. Let's start with one last type of application. So, flip to the previous page. Either of these things, do you think you could solve them to figure out angles instead of side lengths? Yeah, let's try to do it. So suppose I give you a problem like this. I tell you you have a triangle. It has a side length 2, a side length 5. The total area is 4. And I ask you to determine the angle at which 5 and 2 have to meet to make that happen. So what do you think? Could you do that? Let's start by writing down the equation we get. So I guess the area formula says that the total area, 4, should be equal to 1/2 side length, 2, times side length, 5, times the sine of this angle alpha. That looks like an equation we can try to solve for alpha. I guess step 1 is solve it for sine of alpha. And I think I can do that in 2 minutes. So those cancel, and now you divide by 5. Oh, neato. So I want an angle whose sine is 4/5.
Sine inverse of 4/5.
That is certainly the most obvious candidate. But whenever you find an angle using inverse trigonometry, you should ask yourself 2 questions. Is it in the range that's appropriate for this problem? And is it the only answer that's in the range appropriate to this problem? What types of angles can you see inside of a triangle? Like smallest to biggest.
What kind of angles?
Yeah.
0 to 90.
0 to 90. Or this might be an obtuse triangle, right?
1 to 0 to 80.
0 to 180. And like that is the important subtlety. I want angles in 0 to 180. And I've used parentheses because I probably don't want an angle of 0 or an angle of 180 on the nose. Those would be too big. And let's translate back to radians, 0 to pi radians. What's the range of inverse sine?
Negative pi over 2, pi over 2.
Nice. So, this equation is only going to get me, so if I take here y equals 4 over 5, that's going to find for me that angle. This one is going to give me sine inverse of 4/5. Is there another angle that also has a sine of 4/5 in that picture? Oh, cool. What is it?
Pi plus sine.
Not quite.
Or pi over 2.
Nope.
Pi minus.
I hear a pi minus. Yeah, it turns out that's the one. No, remembering exactly what symmetry to use is always something that you should like carefully double check even if you're really confident, because it's really easy to like get the wrong thing. Oh, cool. So I guess there are 2 different candidate angles. In fact, whenever you use sine to solve for an angle in a triangle, you need to worry if that angle can be obtuse, then there's a second candidate that inverse trig won't give you. And that's what we'll spend a lot of tomorrow on. Ooh, so I have my like extra long office hour today, right? Anyone plan on coming and talking to me? Cool.
For the last week we did that other thing in class.
Uh-huh.
How do we turn that in? Because we don't have it for. They said you have to have something with you to turn it in.
Wait, you were in a group, you turned something in.
We turned it in class, but we
Oh.
signed it online. We did something, we turned it in, and tell them to print it.
don't worry about it. I have yours. I haven't like done anything with it yet, but yeah. Thank you. There should be a note in there that says if you taunted it in porcelain, I have it. It'll get graded.
Check 12 thing, something with the 12.
Yeah, that one. Yeah, you were in class though, right?
Yeah.
Yeah. So I have something with your name in it on it already. I just haven't done it yet.
Oh, yep.
Have a good day. Thank you.
You too.